My name is Dan Adams, and I'm a design technology specialist, but I'm also a licensed architect who specializes in visualization and technical storytelling. So I'm going to go ahead and share my screen here. All right. So today I'm going to talk about BIM Beyond Design. That's going to be design technology and concept about vertically integrated manufacturing. So before we dive in, I just want to set the stage with an introduction about my approach to BIM. I just want to make sure, can you guys see my screen?
We sure can.
Okay, excellent, excellent. So I have a long-held philosophy since the advent of BIM kind of showed up in our industry, that AEC tech kind of follows a pattern I've referred to as hub and spoke. I really believe that this is the pattern that kind of defines how virtually all design technology is used in practice. The majority of architecture and engineering firms heavily utilize these design and documentation spokes, and construction, the coordination spoke. The other fringe spokes are used to a lesser degree, but still have a very large impact, which is what we're going to talk about today. So over the years, I've seen these fringe areas. There's a big lack of consistency due to variation in skill sets, different workflows, overhead, evolving tech, etc. So like I said, my primary specialty is in the visualization spoke, but I have a depth of experience in each of the other areas through different roles I've held over the past decade. So today I'll provide a kind of a high-level conceptual introduction to vertically integrated manufacturing and prefab of light gauge steel panels and trusses. So I spent about a year with a light gauge steel manufacturer building a BIM workflow for kind of a vertically integrated manufacturing concept. So that meant engineering, detailing, fabrication, and installation was all handled under one umbrella. And this provided a very interesting opportunity to leverage BIM across multiple stages of the typical project lifecycle. So BIM played a crucial role in streamlining the process by functioning as the primary tool for authoring and tracking fabrication data. So the vertically integrated concept kicks off with engineering via design and documentation, which is a pretty typical place for the structural phase to begin. So structural design marks the start of this manufacturing process and kind of sets the tone for the remainder of the project lifecycle. So for those of you who have worked with light gauge steel before, the first step is outlining the requirements and various light gauge steel components. So to dive a little deeper, vertical integration in this context means that as structural details are developed, they're actually directly informing means, methods, and materials. So this is very different than traditional project delivery, where liability exists in silos between A, E, and C. And there's limitations on how detailed the instructions can be during a handoff from one party to the next, which is often through kind of general typical specs or generic details. You often hear architectural drawings are just referred to as, diagrams. The contractor is responsible for actual means and methods. So in this case, there's a major divergence from traditional process, which will start to become clear as the engineering progresses. So this is an image of a wall panel, and it's just a small sampling, but it does show several different components integrated under this umbrella. So you have your stud gauge and sizing, so your profile sizes, 18 gauge, 20 gauge, etc. Stud spacing, which is 24 inches on center as shown. Horizontal bracing, mid-span of studs. Your king studs, which they can change depending on structural loads. Shown here, they're double kings. The header configuration, sizes, gauges. And another seemingly small but significant item for coordination, especially at this stage, is actually pretty easily handled in BIM. And that's going to be trusses bearing directly on top of vertical wall studs. And that really helps improve the structural quality and performance of light gauge steel. So structural details being modeled in parallel with documentation not only helps ensure more completely engineered structure, but also tees up the next stages of development. So the next step in the process is usually truss design. And there's a multitude of ways the industry approaches this stage, but typically it's handled by an independent truss supplier. But that's not the case with vertical integration. So this example shows long span trusses for a sloped roof. They're designed, detailed, and prepped for fabrication in the same model that was used for early engineering. Some truss design tools inside of Revit, things like MWF Truss Designer, can give real-time feedback on configurations. So quantities can be extracted and used for estimating, ordering raw materials. Mechanical clearances can be incorporated into truss designs and provide downstream coordination benefits. Direct feedback on load paths and how it's going to impact wall panels. And some other benefits, so like considerations made during the design process of the trusses can be carried forward all the way to fabrication and even installation. So that helps reduce information loss thanks to the elimination of handoffs to third parties or independent suppliers. So the consolidated liability, engineer, manufacturer, installer rolled into one, allows means and methods for prefab to be explored virtually with installation crews prior to delivery on site. So the example here is a two-way cantilever truss condition. So even complex situations such as this can be carefully thought out and designed in a controlled environment. So by designing trusses in place with the BIM model, there's a high amount of efficiency thanks to real-time feedback against the architecture model. Things like fascia depths, overhangs, slope, etc., things like that. So uncommon and unique conditions can be vetted to ensure problems during installation are minimized. So after design and engineering, the next stage is detailing and coordination. This is the stage where you start to see the compounding benefits of this vertical integration. So BIM models now have trusses and framing modeled per the engineering requirements, and they exist sort of as like a digital twin, except the other way that would normally be configured. So as most of us know, framing follows the actual construction. Framing will follow slabs and foundations. So traditionally, the lack of a framing model in BIM and the speed of this stage means coordination pretty much just doesn't happen at all. And issues are dealt with as they arise in the field, or things are constructed and you backtrack, kind of repair and replace. So by marrying a scan slab with a framing model, you can actually avoid slowdowns during installation. So anyone who's been fortunate enough to kind of work with a scan of a slab or a concrete pour knows there's a number of issues that come up and that can be addressed. Things like floor flatness, plumbing and electrical stub-up locations. So this image shows the coordination between steel and plumbing. So you can see the plumbing stub-ups here. So most importantly, there's no conflicts with vertical studs. And like I mentioned earlier, studs are often aligned with trusses, so that can cause serious problems if they need to be modified or moved. Second, alignment with bottom tracks can be verified, which anyone who's dealt with framing kind of knows that can be a big issue. So you can actually see here, there was an issue with a sanitary main on the right, and that was actually crossing over the track, but it can be caught early before steel is complete and delivered on site. So another benefit is design and coordination of anchor bolts. So they're usually not considered to a great extent prior to construction in the field. So prefab of wall panels means there's very little room for error during installation, and a single misplaced bolt can cause some pretty significant delays, which negates the primary benefit of prefab, which is saving time. So to avoid issues, anchor bolt coordination can streamline installation. So usually risk of advising on means and methods, that's where that would come up with anchor bolts, but that's effectively eliminated due to vertical integration. So the exact locations of bolts can be specified. Something like using screw anchors can reduce coordination between slab pours and framing installation. So that's typically a pain point with cast in place anchors because they can conflict with vertical studs and door openings. So that would be a situation where field modifications would be required, which again slows down construction and or could impact the quality of construction. Extremely tight tolerances can be achieved, as tight as 1/8 of an inch. Hold down locations can be anticipated and identified well in advance. And the stud tracks can be pre-punched at each bolt location, which eases the process of mapping out bolt locations in the field. So throughout the BIM process, Dynamo plays a very important role. For those of you who are already familiar with it, you already know that the possibilities and use cases can pretty much seem endless. So in this particular case, it was used in a few key ways, such as expanding the functionality of Revit plugins, such as MWF, and improving their integration and communication with Revit. Used to generate CNC files, data mining, large volumes of data from the 3D assets, which can be used for estimating, material takeoffs. And my personal favorite, automating the placement of anchor bolts and communicating with MWF to generate service holes. So Dynamo is definitely an important tool. So
you're here.
So design technology keeps improving, providing us with new tools. So I'm sure we're going to see an evolution continue in manufacturing as that starts to catch up and learn how to use a lot of the tools that exist in AEC. So that wraps up my introduction to BIM and manufacturing. So hope you guys enjoyed it. And any questions?
Very much enjoyment happening. I will tell you from the chat happening. I don't even know how to sum it up, to be honest. And not necessarily even you, maybe even Steve or Scott, if you want to add into this. It seems like there's a lot of discussion in terms of, maybe I'll get to that in a second. Let me get to the more pointed ones. Can fabrication use this application to develop their shop drawings?
Yes.
Let's start there. Yes.
Yep. Absolutely.
We had a question that from David, who asked, we use cast in place anchors for our curtain wall all the time. Does this become an issue with other trades?
That's where at least being part of the discussion, it puts it out in front. So now it can be discussed and planned for accordingly. So kind of broad stroke, taking a different approach because construction and engineering are all kind of in the same team. That's where trying to find a different approach to anchors, either through an epoxy bolt, if you need something that's kind of added after the fact, that can really improve that coordination of bolts just to kind of minimize and make sure everything slips and locks into place.
And I love that you're thinking about that, you know, how everybody on the team is affected. So that's really important. Do you have any data on how much labor does it save compared to the traditional coordination process?
That's a good question. It's always hard to quantify because it's kind of rolled all into one process. So it's happening just kind of as design documentation and detailing is running. So I don't have an exact number on it, but I would have to imagine it's fairly significant. And being an architect, I've always tried to take that approach of trying to think through construction while working, because then that helps kind of minimize any required downstream coordination.
How do you deal with field fixes?
Traditionally, just kind of the same way you would anything else. But having structural engineering on the team, that gives you the opportunity that if a unique fix is required or it's a very tricky situation, you at least have the right people in place to kind of think through and develop a solution that can be structurally approved and blessed for the field.
So getting to the bigger topic at hand, it seems like there's a giant discussion here within the chat about, really it comes down to the level of detail that we typically provide in construction documentation and the scope of our work. And maybe Scott, this would provide a perfect segue into your presentation or even just to a larger conversation. But can you talk to that a little bit? Like, where does that line fall, right? Like typically as structural engineers, architects, we're not for many reasons, going to be modeling to that detail, right? Mark threw in there like, oh my gosh, I can see the Revit model getting bigger by the second. Not to mention the liability side of things. So can you talk a little bit to this process and this integrated approach?
Sure. Yeah. So that's actually been something in the forefront of my mind. Being kind of recently licensed, going through that whole process, learning about much on a deeper level about liability. But I've seen that pretty much the entire time I've been involved with BIM, that there's really a limit. And that's why I kind of referred to it earlier as silos. The A, the E, and the C, it's so heavily partitioned. And the way the contracts
to the owner and the
Yeah,
use
absolutely.
of the building, the
Yep.
maintenance.
And the way contracts are written, the way liability splits are, just even the traditional construction process. Even though we think we've made leaps and bounds with BIM, really, if you break it back down to the contracts and where the lines are drawn, I think that's truly right now in today's day and age the biggest limitation on BIM, because architects, even structural engineers, it's kind of a limitation on how much you're going to put in BIM, because at the end of the day, you have to consider profitability, and you can't just do things for the sake of doing them because they're interesting. So the project would have to be structured from the get-go with contracts and liability to kind of work with this new system. So rather than architects and engineers providing diagrams for the contractor to build, and I've worked in the general contracting side as a coordinator, so I've also seen in the other end taking the diagrammatic models and turning them into real models based for fabrication. Just that disconnect, there's so much inefficiency, but it really all stems back to the liability and the way the contracts are drawn. So I think once we see a big evolution in the liability side, that's when I think we'll see real changes in how BIM can actually be used, and we can start pushing the limits on efficiency and kind of cross-pollinating between disciplines.
And kind of this idea of the model being the deliverable in some way, right? And like this idea of almost a digital twin as you're going through design, but also through construction, and informing that model back about what's actually happening, and then thinking about how maintenance and the building owner can utilize this data later.
Exactly. Yeah. Digital twin would be beautiful. It's a beautiful concept, but because of that liability split, we just can't quite get there.
Exactly. That is a presentation in and of itself.
It certainly is.
Well, thank you so much for your time, Dan. And of course, please feel free to throw additional questions as they come to you, and we'll have a chat at the end.